Thank you.
All right.
Is that the most you've actually read of?
Average acceleration. All right, we'll talk about acceleration. Average acceleration. This will be the last thing on your test. Okay? Monday. It's average acceleration. All right. Obviously, average what?
Can I go to the UAB thing that's called for?
Are you supposed to?
Have you signed up for it? You definitely have to sign up ahead of time. There's like a little thing. I mean, if you need to go, you definitely could ask, but
I go up there and ask?
you can ask him and he can say yes or no.
Are you going to go? Are you interested in UAB?
Yes.
Okay. Good school. I like it. Note. Bring me a note.
You probably need to go to Miss Mendez.
Yes.
And get a note from her.
Get a note. All right. So we talked about our acceleration graphs. All right. Average acceleration. All right. That is any change in velocity during a given time period. I'm going to show you how this works, and we'll do some little things in here where we'll figure out average acceleration later. Remember, our average, and keep these straight. Average velocity is our change in position divided by time. Average acceleration is our change in velocity divided by time. All right? So keep those straight.
What would you say?
Okay? And that's, do what?
Can you repeat that?
Average velocity. Do I need to write it down so you can copy it? I know I've written this down. You've got this in your notes.
You have it in our notebooks 2 times already.
Thank you. That's okay. Look, it's okay to be redundant and keep saying it over and over and over. Because listen, once you get into the test and you have a test on this stuff and there's a graph and you're going to go, do I need average velocity? And you'll see this test is not heavy on it, but later down the line, I'm going to want to know, I'm going to give you a word problem and I'm going to want to know average acceleration, but I'm only going to give you velocity and displacement. Okay, or I may only give you displacement and time. And then you've got to figure out average velocity. So let's write it down again. Average velocity is displacement divided by time. All right? And we can do that. Change in position. All right? Over change in time. All right? Change in position is always going to be x final minus x initial over time final minus time initial. All right, that's always going to give me my displacement as long as I have that arrow up there. It tells me a direction. All right, so let's say, okay, Davis runs for a touchdown, picks off the ball, runs for a touchdown. All right, and he runs it in from 25 yards out. All right, so we look at where he caught the ball right here. He's an X because he plays on defense. All right, and here's our football field. 5, 10, 15, 20, 25 yards. There's touchdown right here. There's goalpost back here. All right, picks it off here. He runs over here, spins around the guy over here, runs in the end zone. All right, now his displacement is going to be if we're just looking at the goal line, his displacement would just be where he picked the ball off from to the goal line. So that would be 25 yards. All right? We would not count all this in his displacement. All right? His displacement is from here to here. That's all we want to know, how far it took him to get from the 25-yard line to the goal line. All right? So his initial would be the 25. All right? His final would be the goal line, and we'll call it 0. All right? Because the offense goes this way, right? All right? So that way we could get our velocity to the goal line. So 0 minus 25 is negative 25, right? That gives us our displacement. And let's say it took him 8 seconds, okay? Time initial was 0, time final was 8 minus 0 seconds. Time only goes in one direction. All right, we'll make it easy, okay? I want to make the problem easier, so we'll make it 24 yards. All right? 8 goes into 24 how many times? 3. All right? So his average velocity, all right? Average velocity equals 3, and then we have to make sure we put our signs in here, 3 yards per second. All right? Or sorry, negative 3 yards. Because we determined that this direction was positive to begin with. All right? Because he plays what? Defense. All right?
Is the goal line 0?
So the goal line would be 0.
Okay.
Okay? The goal line would have been our 0. It can be either way. We can do it either way. And we determine that. As long as we predetermine it, and this is where it gets tricky in problems on tests. Okay? You've got to know all of this information. What is the positive? Well, the positive is the direction the offense is going. They're going out. Okay? We're calling that the positive direction. They're going towards their goal line. All right? They're obviously a long way from their goal line if he's picking the ball off on the 24-yard line. All right? They got at least 76 yards to go. Right? He picks it off, takes it in 24 yards. All right? So now we've got the negative. All right? You understand? So we're starting at the 24, we're going down to the 0. When he crosses the 0, we're good. But we're only counting, we're not counting all this, where he ran into this guy, spun off of him, ran around that guy, juked here, broke some guy's ankles, and ran into the end zone.
So basically, they're going off.
All right? The O's are over here. They're going that way. All right? We determined that the offensive movement was positive in this case. All right? And it doesn't matter which one we choose, but once we choose one, we keep it that way. Okay? Once we choose it, we keep it that way. The offense will always be the positive direction. The defense will always be the negative direction. Okay? And that's just in this problem. All right? That's just the way we set it up, as long as we do it the same way every time. All right? We could have done it the other way. We could have done it the other way. We could have said, that he picks it off at 0 and runs it 24 yards to the end zone. We could have done it that way too. And we come up with the same thing. All right? It just would have been a positive instead of a negative. But as long as we determine what it is, we're good. And that's one of the things you get to kind of decide that. Now, in problems, when I do a problem on a test, you're going to want to read it carefully to make sure, like if I say a helicopter is hovering, that means it's doing what?
It's only moving up and down.
It's only moving up and down. Okay? So even though he may be very fast through all this, his actual progress to the goal line was only 3 yards per second, which ain't real fast. All right? Again, displacement is all we're worried about. From here to here. Not worried about all this other distance he ran. All right? Does that make sense? You with me?
Yeah.
All right? So that's average velocity. All right? Now, if we had someone with a stopwatch taking times at each one of these spots, we could figure out his average velocity because his average his average acceleration, because his acceleration towards the goal line changed, didn't it? Why? What three things change acceleration? All right?
Changing velocity, changing direction, changing speed.
All right? Good. Hang on. We'll get to that. We'll throw that up there. Let's do this real quick. Let's go back. Let's make sure we got this. Average acceleration is, what did I say? Changing velocity over time. All right? Change in velocity divided by time. So to get average acceleration, we're going to need different acceleration. We're going to need more spots in time to be able to do that. Now, there are times when we're going to have constant acceleration. Constant acceleration is always going to be that straight line. All right? We can get that really easy. But you're going to see that acceleration is not always constant. All right? And velocity is not always constant, so we're going to get some of these. For example, hold on examples. Okay, don't go too fast, Anderson. All right? So, change in velocity, all right, over change in time equals velocity final minus velocity initial over time final minus time initial. All right? How many times have I already put that up there?
3 times.
3? Okay.
That? Wait, oh yeah.
Average acceleration. I don't think I've done average acceleration.
You did it twice on the day you did the graphs.
Yeah.
It's like just.
Okay. Repetition is not bad in this case. I know some of y'all like, get it. First time you go, oh, that's simple. Okay? I get it. Okay? It's just like coaching football. All right? You can go out and tell one group of guys, hey, all plays that go to the right, they have they have even numbers. All plays go to the left have odd numbers. We actually flipped it one time one year, and it worked great because we could call plays at the line. They were going, it's going over there. Nope, it's going over there. It's awesome. We'll go up the line and just call 13. Linebacker stepped over. Right there. Gone. It's great. But anyway, some people need more repetition to pick those things up. Okay? Some people need more repetition to pick those things up. All right, now, average acceleration is best when a specific time period is needed or a distance. Okay, we'll do this. We're going to talk about how far a plane has to travel in order to take off. All right? But if you look at, and we kind of drew it up here with our interception for a touchdown, average acceleration is most useful a specific time or distance is needed. And this is what we're going to find in engineering. you'll use a lot of these average acceleration problems when you're trying to figure out how far or how fast something has to go in order to reach a certain velocity. How far does a airplane have to go to take off? How far does a car have to go to reach a certain speed? All right? That's when we can use our average acceleration. We'll do one. I've actually got a problem that we're going to do together in class where we're going to look at how far an airplane has to go to take off, given its specific trajectory. Then we're going to add in some things like, well, there's a force of wind moving on it, and there's winds moving against it at 1 kilometer per hour. It has to reach 283 kilometers per hour to take off. How does that wind affect the takeoff distance of that plane? All right. Do what?
Wait, are we assuming, would that be assuming that are we calculating how much more power it needs or how much farther it would have to
How
drive?
much farther it's got to go?
Do you measure distance and power, Jonathan?
No, I'm saying is that if you increase the power, then you might not have to go as far.
You can't increase the power. The power is what the power is. Power is what the power is.
I mean, think about running jump. If you have power,
Well,
better
you
jump, you don't have to run as
power
far.
because you need the fuel to go.
All right, we always measure acceleration in meters per second. So let's do a little.
Per second per minute.
Just stop. All right, let's do a little.
No, he does not have.
Little time velocity thing right here. All right,
Don't touch the brain.
this is my velocity. All right, this is my time. All right.
That is not what I said.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12,
Like, you know, you should get a section sheet. That'd be cool.
5, 6, 7, 8, 9, 10, 11, 12, 13.
I'd be down. So we're, you know, through this body.
All right, so I have an object, all right, and it's moving at, these are going to be meters, and of course this is seconds. I have an object, and it's moving at 3 meters per second, all right? It's moving at 3 meters per second, so, and that's going to be my 0 time, okay? It's going to be at 0, all right, 0 seconds. And when we pick it up, it's already moving at 3 meters per second. All right?
How many lines do you have?
I think I've got like 15 and 20. All right? That's its initial velocity. And remember, this is V. Okay? It's my velocity. Not saying where it is. We're not looking at it in space. We know that it's moving in 3 meters per second to the east. Right? Huh?
To the negative west.
To the negative west. All right, it's moving at 3 meters per second to the east.
Negative.
All right? It stays at 3 meters per second to the east for 3 seconds. All right? All right, so it moves at 3 meters to the east for 3 times 3 seconds. So we can set this up. 3 meters. 3 meters per second to the east times 3 seconds. Okay. How far is it going to travel? 9 meters. So now I know it's going to move at this constant speed for 3 seconds. Alright? Now, because I still have a flat line, I still have that horizontal line, where can I find my distance traveled?
Multiplying the velocity by the time.
I can. And what else? I also have a neat little geometric progression right here. It is actually the same as the area under that particular spot. All right? Now, at 3 seconds, it is going to accelerate. At 1 meter per second, okay, it is going to increase its acceleration at 1 meter per second for 10 seconds. All right? So now it is going to increase its velocity 1 meter every second. So I know that at the end of 4 seconds, it's going to be moving there. It's going to be having an acceleration there, right? Its velocity is now going to be 4 meters per second. At 5 seconds, at 6 seconds, at 7 seconds, how many seconds did I go for? 10? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right? And we have a constant acceleration for 10 seconds. How fast is the object going?
It is going. You are right there.
What is its new velocity?
After how many seconds?
After 10 seconds.
13 meters.
What is its velocity now?
Would it be Q? I mean like exponential. I mean not. Exponential.
This is a very simple problem. Now let's remember.
Initial 3.
Oh, I did pretty good there.
What is that stuff?
What is it? We're average of 3.
What's that?
Should have been right there. All right, this is a straight line. Okay, for 10 light, that's a straight line. This is a straight line down to 10. All right. What is its velocity now? Well, this is a pretty simple problem. If it's adding 1 meter per second for every second, it started out at 3 meters per second. The magnitude now is what?
13 meters
30.
per second.
Wait, for
13 meters per second.
for 10.
Okay?
You're adding 3 every second.
Adding 1 every second.
Oh, 1. Okay.
All right?
Okay.
Started out at 3. All right? Now, this is another one of those great, wonderful geometric things we get. All right?
It's 1 meter per second.
We've still got
3.
this right here. Okay? My speed is still, or my velocity is still going to be the area under this triangle. All right? And rectangle. So here we have 10 times 3, so that's going to be 30 is what my area is going to be. And this is a triangle, so it's 1/2. Okay? The base times the height, right? My base is what? 10. My height is 10. All right? 1/2. 10 times 10.
20. Or 100. Or
Yeah, 10 times 1/2. 10 times 10.
50. 100.
100 times 1/2 is 50. That's going to tell me how far I've been. All right? I have been displaced now. My change in displacement, my change is going to be 80 meters.
Wait, where'd you get money from?
Where'd I get 80 from? 1/2 base times height here? It's 50. Plus my 30 is 80. All right? So I can now tell how far I've gone. Gone 80 meters. Figuring out the final velocity is not that hard. Figuring out how much distance I've traveled is. All right? Because understanding this, and this is just an example problem. This is where we're going. All right? This is the direction we're heading. Knowing that all of these little geometry rules work for us to understand the distance. So out of this one graph, now I can get my displacement. All right? I know that I started out at 3 meters per second, or sorry, 3 meters at a constant movement, right? So there's my, actually it's more than that because I have to add that 9 in right there. So from my initial time, I've actually gone 89 meters. From the time I accelerated, from this time, it has now moved 80 meters.
Does it also work if you just subtract the area outside? So like you can make a projection to make one big square and then just subtract the area of 2 triangles. Does that work as well?
Yeah, you're doing the same thing.
Yeah. I mean, it's just more efficient because you only have 2.
Well, you've still got this area you've got.
I mean, yeah, but you have to only
That
find
makes
the
you
area
saying-
of 2 shapes instead of
Maddox
3.
is saying a triangle and a.
Well, yeah, but you should already have this one.
Oh, Maddox is
Less
saying-
work to be shown.
Maddox is
Yeah.
saying.
Maddox is trying to get out of doing more work, is what he's doing. All right?
Wait, and you got the, and it said it went, you gave us 10, right?
Well, where did the 10 come from? It
Right.
went 1 meter per second for 10 seconds.
Okay, that's what
It increased in velocity.
Okay.
Now, we're going to say at that point velocity eases off, okay, and we've reached our final velocity. All right? Now, this is the kind of thing that they have to do when they start deciding how long to build a runway for an airplane. We're going to do one of those problems. We're going to try to figure out how long it's going to take us to build a runway to get an airplane in the air.
Wait, how long?
All right? How long the runway's got to be.
Or how long we're going to
All right?
build a runway. That's a very good question.
Do what?
No, this is what he said.
It's like that one that says,
So, let's look at one that's a little bit different.
he does.
I'm going to give you the numbers, and you're going to work the problem out. All right? Car is moving at 4 meters per second. East. All right? The car accelerates to 36 meters per second to the east in 4 seconds.
To 3 meters?
You have 3 meters.
36, sorry.
Fast car. Fast car. 3 meters per second. In 4 seconds. Dang, that's a world record, I think.
What is its average acceleration during that time period?
What was your question? Sorry.
Car is moving at 4 meters per second to the east.
Yes.
The car accelerates to 36 meters per second to the east in 4 seconds.
Yes.
What is its average acceleration?
like 7.5 something.
It's 8.
32. Oh, yeah, I thought, it says 8. 8 years per second. It's 8 years, you're calculating, you forgot to subtract the initial 4. Yeah, because it's already going forward, it's acceleration, not from 0. So that's what.
Your VI is 4, not 0.
So, but so that's
-8.
positive 8.
I got positive.
Positive 8.
Oh.
I'm accelerating.
Anybody want to go up and do the problem on the board?
I mean,
Well, then why is
Joseph,
it
you
4
want to?
TI?
Joseph really wants.
I love
Huh?
Why is it 4 TI?
Because it's already been 4 years.
Time initial is 0
Oh, alright.
here.
What would you be doing?
I don't know, something to make a lot more money now.
I'll do it.
You gonna do it? Go show us.
The shape.
Graph, either one.
Oh, I can do a graph.
Alright, somebody want to go up and do the graph?
No.
Somebody go do the graph for me.
I don't think anybody did the graph.
Do the graph and show me how far it went.
It's locked in
Do I have to do the units of meters per second?
Yes, make sure you label everything.
Not the squiggles.
Alright, no, it's not X, it's V.
Oh, it's 3 hours.
Yeah, that's what, listen, that's a common mistake. It's not a big deal. I do it too, I've done it too. When I took a couple courses this summer working on this stuff to get refreshed on it, I did the same exact mistake. I would put X over there instead of V, and then I'd look at why I got it wrong. I was like, I know I'm right, the numbers would be right. I got the darn trajectories wrong. I got the units wrong. All right, velocity final minus velocity initial, 34, 36 minus meters per second minus 4 meters per second. It's 32 meters per second over 4 seconds. Its average acceleration was 8 meters per second per second. Excellent. What's missing? There's one thing missing on there. Not, Jonathan, you get busy on yours. What's missing? Direction. All right? We need to give it a direction and an arrow. All right? So that we know it's a vector to the east. All right? The math is right. And guys, the math is sometimes the easy part. That's not hard.
Is that right?
That's right, it's perfect. Now, the one thing you left off, it's a vector, so it's got an arrow. And I need to know the direction, it's to the east.
Wait,
Actually, your final one's going to be 36.
yeah, that's what
It accelerates 36 seconds, 36
Okay.
meters per second.
Oh, I'm not wrong. That
I
doesn't
put
say if it.
And that's going to tell us how far it went.
Oh, wait. It's base.
1/2 base time height.
36 times 4, which is 18 times 2 is 36, 72, 36, 1/2 base times height.
Now you got 36 meters plus you have to add in what's below.
Alright, plus already 4, plus 40 meters per second. Wait, yeah, because we're doing
Now, this is distance.
Oh, that's just, yeah.
We can figure out the displacement.
40
Is he doing the same problem that Mallory did?
Yeah, it's the same problem, he's just doing the vector. He's just doing the displacement.
Is that right?
Sorry, I see Jackson with this right
It's Jackson Lucas and Who do we vote?
I bet it
for
is.
now?
So that it's.
I was gonna vote for Clay, but he was at Oscars.
Yeah,
He was?
Yeah.
Oh, I forgot about that.
Now, the thing is, and this is common again. Now, watch what he did right here. Even though his final is at 36, yes, but his initials at 4, so this actually should have been 32, okay, times 4, which gives us, what, 32 times 4? 128
So it's just 30.
over 2 is 64.
No, that's not right.
That's not right.
64 is 64 is
Just
128.
divide those by 2 already, so you get 16 times 2, which is 32 versus 32.
Okay, 32.
Oh yeah, I'm going to Panera.
Because that becomes, because that, because you just go ahead and divide them individually and then multiply.
Okay.
I knew it.
All right, so we get 64. All right. 32, we know it covered 40.
I was thinking about it.
And we know that it covered 72 meters. All right? We know that it covered 72 meters during that time. 72, because you can't forget.
So do we.
Oh, sorry. What do we got at the bottom? 4 and 4 is 16. Sorry. 16. So it would have been our 32 plus 16.
Who was it for?
48. 48.
Oh, since the baseline height is also divided.
Well, now the bottom you have to do with the rectangle. All right?
So I have a
Still
question.
baseline.
On the test, if we have a question like that, are you going to specify if we have to do the graph or not? Because why do the graph and that math is so much easier?
All right. That is to find the distance we covered. Okay? You're going to need to do that if I want to find the distance. All right? Because I need to know what the initial was. Okay? My initial is 4. I go 4 meters per second for 4 seconds. I'm going to cover 16 meters. All right? And then I cover 32 meters in the last 4 seconds, or in the same 4 seconds, at an acceleration of, what was my acceleration factor? 8 meters per second, all right? Then I can do my 1/2 base times height, and I've got my base is 32, okay? My height is 32, my base is 4.
Okay.
Okay, I was saying, wait, your what? The height?
The height of the triangle.
So then 32 times 4.
And it's also going over 1/2 base height of my triangle.
You don't divide the bottom one because it's a square, not a.
Right. It's a rectangle. And that's really the easiest way to find the distance covered. This tells us the acceleration factor.
What?
This tells us how far the car went. All right, but we can also use that. I mean, it's very simple to plot it on a graph as well. All right, and then all I have to do is count my lines up, count my lines down. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I know that if it's going, 36 meters per second at the end, I know what the acceleration is at the end. I know what my final velocity is. All right. Did you make it in? All right, questions about any of this? Yes.
I understand up until the
All right.
Might also, if you, my numbers might, my numbers still being up there might not.
Yeah.
So.
All right. So here's my problem.
You got public school on 48.
Now remember, this is velocity. All right. So, I mean, 4, 8, 12, 16, 20, 24, 28, 32, 36. My initial velocity is 4 meters per second. All right? It accelerates for how long? 4 seconds. 1, 2, 3, 4. All right? So at the end of 4 seconds, I know I'm going to be at 36 right here. Is that what I said? 4, 8, 12, 16, 20, 24, 28, 32, 36. So I know this final velocity is going to be 36 meters per second. All right? Now, all I've got to do is draw my triangle. Now, I'm starting at 4. So I'm going to take that across, all right, make a straight line. I know this is one section of it. I know that for 4 seconds, my unchanging part of my velocity, okay, is going to be 4 times 4. And that's going to equal 16, right? The area of a triangle, what's my formula? 1/2
Times base height.
times base times the height. All right? So my base is 4. All right? My height is my initial velocity. All right? Or sorry, my final velocity minus my initial velocity. So that's going to be 32. All right? Divided by 2.
All right, Vikings, it's time for prayer. In the name of the Father, and the Son, and the Holy Spirit. Amen. Bless us, O Lord, and these thy gifts, to are about to receive from thy bounty through Christ our Lord. Amen. In the name of the Father, and the Son, and the Holy Spirit.
Where did you get 16 from?
Teachers, would you please release me here? Thank you.
Right. You don't divide by 2 because it's a square.
Right, 16 is the whole thing. Because my initial was 4. That's where I've got to go across. So
do you have all of this?
I want to add this in. I'm already going to be complete.
So after you get
Right? And then I would add in my 16. Covered 80 meters.
Goes around one end. That is that. Letting it in. That's letting it out. And kind of like that. And then height. And then kind of connect them all together like that. So then
You can make it all one. That's better.
and then so it would have to be connected by a band. I mean, it would only be one because they're already connected to begin with. So it wouldn't have to be. I think this would have to be shaped a little differently. At least the top one, because it would have to allow for more than average, more than normal fuel to go in because it's.
Thank you.
All right. Good lunch. Good lunch.
Should it?
You can make it work, yes. Once you figure out what you were doing.
So I said it's time to figure it out. Is there any recycle thing?
Come on!
All right.
Oh, yesterday I used the baseball thing.
Oh wait, we have to call it today.
At first the button.
64 plus 16 is going to get us.
Call mommy knew.
Oh yeah, we were joking.
That's our total distance. Because remember, we were initially already assigned
So,
so we've got to add that in.
Which one?
So it's 4, and that's how we get our triangle. Right across the okay, we get our triangle.
Little did you know.
This distance in. Because we were already moving at 4 meters per second. Okay, and this is just additional to what would have been our constant velocity if we had remained at a constant velocity.
Oh, okay.
Got it?
That makes sense.
You're welcome.
boards for lunch. Freshmen, you will be released at the bell. Thank you.
So we're trying to watch the finals while listening to the story. And it is packed. I mean, it's completely packed. But it was painfully comparison to that story.
I need to go. I love you.
My legs hurt so bad. Huh? I don't know, it's like my muscles. It's like I was working out or something, which I went on a rant.
What's that?
I didn't even see
What's
it.
up? You said, give me his spirit, what? What's
I don't even know who that is.
I think he let you.
Ooh.
But I was right, so did he asked me in the poster. Oh, he did? Yeah. What did it say? Girl, nobody here. Hell, bro. You so hell. No, I'm dead. Like, I was already crying. I was already crying. And so I was like, oh my God. Do you have it? No, it's in his trunk. I didn't want to carry it around. And put it in my office. You didn't take a picture? No, I was supposed to take a picture at the end of the day. Because I got work. But this shit was fucking funny. Look at this, look at this, look at this. Hold on.
I want smoke.
Ew, baby daddy thought. Look. Hunter, what'd you do her? Hunter, what'd you do her?
Yeah.
Would you?
Look, kids.
Oh, he is in your baby daddy.
Spray it after last class. If you want to spray them again, go ahead. If you want to spray it again, go ahead.
Mr.
I spray them after the last class.
Real quick.
Run.
My back speed.
Quit shuffling your desk around. It's driving me crazy. Move this straight. Come on.
I'm visual.
No.
No, okay, the first part is that eat and really
Shut up.
something.
It did.
He did? Yeah.
It did.
It was surprisingly me, but go on to the camera.
All right. Let's see. Let's figure out who's here. Who ain't here? Somebody finds my glasses. That would be great. That would just be awesome.
Hey, Ben. Hey, you just mad you can't watch anything during class. Hey, keep watching, Ben, I'm gonna watch.
All right, let's see. Taylor. Online. Sydney.
Yeah.
Casey.
Yeah.
Alex.
Here.
Ben.
Here.
Sean.
Here.
Sean.
Here.
Frank. Here. David. DeWitt. George. Here. David. Cucker.
He's not here.
Check that. Luis is
Hobby.
Hobby.
Luis, I'll be in the radio.
All right. Anissa. Caleb. Nine. T. Marshall. Hunter. Bathroom. Mark.
Yep.
You go by.
Chandler.
Go by what?
Chandler.
Chandler. And Benny.
You heard
All right. I've got everything like blown up. I can't see Jack.
Oh.
Blind.
I don't like
Grumpy.
I like this.
All right.
I just like
What's up, kids?
So.
All right. Y'all's test is Monday, right?
Yeah, yes, sir. Next Friday.
You said the Monday after next. I said school. Yeah, Monday. And we wait till Monday after next. There really would be a lot of stuff on the test. All right. So I think this is where we left off. All right. Remember that velocity and speed are not the same thing. All right? Velocity has a direction. Velocity has a direction. Velocity is a vector quantity. Always. Needs direction. And we kind of showed that yesterday with our touchdown run, right?
Yeah.
You know, if we ran the touchdown in, you know, it's not going to be a straight line. All right, here's our football field. Here's our football field. All right. And then there's our 10, 20, 30, 40, 50, 40, 30, 20, 10, touchdown, right? And not to draw this, our player catches the ball, right? He catches it at the 1 yard line. He runs this way, he runs this way, jukes right there, runs around a guy, runs over the kicker, and he runs a touchdown. Okay, runs a touchdown back. Now, if we were doing a vector quantity, the only thing we would be interested in is where he started and where he finished in a straight line. All right? The speed may be different all throughout here. Okay? The velocity may be different all throughout there. But as far as a vector quantity, if we wanted to know the velocity, it would just be this right here. All right? And we could do speed and direction and find out how fast he was running to the right, left, but we would have to take all of those vector quantities and all of those changes of direction into account. All right? Very rarely do you see somebody catch one and just run straight down to the sideline or down the middle of the field. Happens every now and then, but very rarely is there going to be something that gets in the way. Well, when we talk about it as a vector, we're talking about a straight line. All right? It has to have a direction to the goal line. All right? So that's why velocity and speed are different. Okay? It has to have a direction. All right? When we talk about constant velocity, all right, that would not be constant velocity. That would actually have different velocities, and each time he slowed down or sped up, that would not be constant velocity. All right? Constant velocity implies constant direction and therefore a straight line. All right? What did I say? Implies constant direction. Therefore, a straight line. We can use velocity and speed, and we can use different velocity vectors for a lot of different purposes. If you watch, y'all watch the weather. I won't watch any. There's no shows I really watch other than The Walking Dead, and I keep waiting for the end of last season. And the only reason I really watch it is because they filmed it in my backyard when I lived in Newton. Literally in my backyard. So I saw all those guys. I got to talk to all of them.
Really?
I got mistaken for Negan one time.
For what?
For Negan.
Really?
Yeah, I was sitting in the back of this place, dark restaurant. It's called, can't remember what it's called. Anyway, I was sitting back there by myself eating, and I was all scraggly, and I had my beard, my hair was all messed up. And these two kids came up and said, I can't remember the actor's name, "Are you so-and-so?" And I looked at him, I said,
Just a yes.
I know I should have. I said, "No, that's not me." And the guy that's the star, the Rick, he's about that tall.
Are you serious?
Yes.
Ain't no way. Are you serious?
Yes.
So he's like as tall as everybody on the set.
Right. That's all. They do angles to make him look as tall as everybody else, but he's 5'4". Now the guy that plays Daryl, he's about 6 feet tall.
No, he looks the same height.
Yeah. But yeah. And what's his name? Lincoln something. He's only about 5'4". Anyway, I got mistaken. That's the only reason I watch it. But I watch the Weather Channel all the time. I like to just watch the Weather Channel. Like, come by and see what's Coach Anderson doing. He's watching the Weather Channel. All right, I'm interested. This kind of thing comes in really important in weather, okay? Because they take all of these velocity vectors into account when they're trying to predict what a storm's going to do. You know, when they're following storms and storm chasers, these guys that get out of these vans and go chasing tornadoes, they have all kinds of equipment in there that will tell them different wind velocities at different levels. And that helps them to get to the spot they want to be in order to see and record a tornado. The thing about it is, it's really, really tricky. And they will occasionally do something like end up in front of a tornado. And, you know, let's get out of here. One group barely escaped death. And there's a great video or TV thing they showed where they just barely got out in time. But that's why we do these velocity quantities, all right? Just like our running back running down the field, they'll check out different vectors of velocity at different levels in the atmosphere, all right? Because the storm may be moving to the east, but there may be a velocity vector underneath it pushing it more south, okay? And so they try to, you know, level these things out to try to predict weather. So that's one of the ways this is really, really useful. Figuring out how long it takes, you know, our kickoff returner to get to the goal line, that's not a very good use of a velocity vector, okay, of a velocity quantity. That's not a very good use of it because it really doesn't tell us anything. All right? It only tells us how long the play took and how many yards it covered. It doesn't tell us really what we need to know. Because if we really wanted to know what was going on, we'd want to know how long it took him to get to this point, how long it took him to get to this point, and that way we might find something, okay? Now, anytime we have a change in velocity, we have something called acceleration, all right? A change in velocity is acceleration. Any change in velocity is acceleration. So if we go back and we look at our touchdown run, we can find our velocity, okay, what his velocity was towards the goal line right there. Well, remember, he started out over here, went over here, ran around a guy, ran over the kicker, and then he ran into the end zone, right? So any change is acceleration, all right? So when he turned, that's acceleration. When he slowed down, that's acceleration. When he sped up, that's acceleration, all right? So there's three ways to accelerate. All right? One, speed up. And when we say speed up, we mean speed up in the same direction. Because remember, it's a vector quantity, so it has to be going in the same direction. So, let's take, for instance, I buy a Porsche. I don't want a Porsche. I buy a 1966 AC Cobra 423, 2 barrels, straight jet exhaust. take the hood down, crank that thing up, boom. And I go from 0 to 60, 3 seconds. All right? So I'm going 0 miles per hour at the beginning. I'm going 60 miles per hour at the end, and I do it in my time change is 3 seconds. All right? So to force that to do an acceleration problem here, I want to know what my change in velocity is over my change in time. And I can figure that out by, if I want to know what my change in velocity is, it is my velocity final minus my velocity initial over my change in time, which is my time final minus my time initial. All right? And my velocity final is 60 minus 0 over my time final is 3 minus time initial is 0. That gives me 60 over 3. And we need to label these miles per hour. Miles per hour. 3 seconds, 0 seconds. Okay, 60 miles per hour over 3 seconds. And that tells me that my acceleration rate is what? 3 goes into 60? 20. Okay. 20 miles per hour, okay, per second. All right? So every second, I'm increasing my speed 20 miles an hour. Now, no car accelerates that smoothly. That would just be my average acceleration. All right? That would just be my average acceleration. But that lets me know that I'm increasing in speed. So if I were to look at my speedometer on this, all right, I would be at 0, 20, 40, 60, and at 1 second, I should be at 20 miles an hour. At 2 seconds, I would be at 40 miles an hour. And at 3 seconds, I would be at 60 miles an hour. And whoever was sitting beside me would be holding on for dear life. All right? Because that's really, really fast. It's a really simple problem to show that. All right, so that would be my average acceleration. Of course, like I said, it's never really that smooth. So I can increase my speed in the same direction. And in that case, we would say the direction would be down the road, okay? East, to the right of the observer, whatever we wanted to make it, but we would need a direction with it, all right? Number 2, we can slow down in the same direction. All right? We can slow down in the same direction. In physics, we say deceleration all the time. We have to make something decelerate. In physics, there's no such thing as deceleration. We say it is accelerating in a negative, to a negative power. And we can see this, we're going at 60 miles an hour. All right? And then we come to 0 miles an hour in, let's say, 3 seconds. All right? So we can do the same formula here. All right? My change in velocity divided by my change in time equals velocity final minus velocity initial over time final minus time initial equals my final velocity is 0 minus my initial velocity of 60. My time change is always going to be 3 seconds minus 0, okay? Took me 3 seconds. My time always goes forward, never backwards. All right, that's going to give me negative 60 over 3 miles per hour over 3 seconds. What does that equal? That's going to give me negative acceleration. So now I'm going to be negative 20 miles per hour per second. All right? And if we wanted to take the hours out of there, we could. All right? We could do the math and divide it by 3,600 and go ahead and do our all the way down to how many meters per second per second. Yes.
Right, brother.
Yeah. All right. So we don't decelerate. We have negative acceleration. All right. And again, it's in the same line. This would be 20 miles, my negative 20 miles per hour per second to the east, to the right, to the down the track, whatever we wanted to make it. All right. Third way we can accelerate. Change directions. Right? A change in direction is also acceleration because it is a change in velocity. All right? Because remember, velocity is only in what? How many directions does velocity have? 1. Okay? So if I change directions, I am changing my acceleration even if I don't change speed. All right? So we're at Talladega, where they got a really big racetrack. Big tri-oval racetrack. Now at Talladega, they don't lift. You know what that means?
They don't slow down.
They don't slow down, man. They don't slow down. Once they hit that corner, they just stay on it. All right, so on the straightaway, my velocity is now 201 miles per hour, okay, to the east. Now, as soon as I change directions and I start going around this turn, my velocity changes because I'm no longer going to the east. My velocity is now moving to the west. All right, and we call that energy around here, that curve. All right, and we'll come to these later. This is called angular momentum. And we'll get to that. Not going to talk about it today. Okay, but now we've got into a thing where we have constantly changing velocity vectors. All right? Because my speed, even though it's not changing, my direction is constantly changing. If we have something, and I had something here a minute ago, there it is. My keychain, my little key fob. All right? We can measure how fast something is moving around a circle. That is only speed. All right? So if I have something that I have right here and I can swing it around, all right, at a constant velocity, or sorry, a constant speed, its velocity is constantly changing. Just like a planet in orbit, because a force is acting on it from the outside. In this case, the thing that is causing that force is the lanyard. It's acting as a normal force against the moving keys. All right? So everything is moving around. I have a constant speed, but I do not have a constant direction. So in order to figure that out, I would have to use my angular momentum formulas to get that vector. All right? But that is constantly changing velocity. Speed's pretty much the same. I think I can get it pretty much, keep the speed the same. But because it's changing directions, it's changing velocity constantly. If I let it go, it's going to go in whatever angle I throw it at, okay? In a straight line until it's affected by gravity, which is immediately. All right? So, let's remember, did you write down the formula for change and acceleration? No, what is it? All right? Acceleration equals average acceleration. Where did I lose you?
The beginning.
All right. Acceleration, average acceleration equals the change in velocity over the change in time. Velocity over change in time. All right? Let's make sure we have all this down. Change in velocity over change in time is velocity final minus velocity initial over time final minus time initial. All right? That all means the same thing. All right? Every one of those means the same thing. Average acceleration is the same thing as change in velocity over change in time. That's the same thing as delta V over delta T. Delta V over delta T is the same thing as velocity final minus velocity initial divided by time final minus time initial. Now we can get a lot of information out of that just by knowing these things right here, all right? And when we put them on a graph, when we look at them in an equation, either way, it's still going to come out the same thing. Oh, sorry. You still need that? All right, hang on. I'll rewrite it. Change in velocity over change in time equals velocity final minus velocity initial over velocity over time final minus time initial. All right. That all means the same thing. And I know your head's going to start spinning because all these formulas look very much the same, don't they? Where do we start moving in two directions? Right now we're moving in one. All right? You with me so far? This means yes, Coach Anderson. We are with you. All right? So let's play with it a little bit. Let me show you some things. You don't need to write any of the following down, okay? All we're going to do is I'm going to show you some examples of how this works and how we can get a lot of information out of it, okay? But do pay attention because this will come back as well. When we do a velocity time graph, All right? A lot of times what we will have to start out with is a displacement graph where we have a change in displacement over time. And we can take this information and move it over here once we figure out what the velocities are. All right? Now, there's some pretty cool things about a velocity time graph. And we can see these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. We'll make it 13. So if I have an object that is moving at 1 meter per second, and velocity is always written this way. Velocity is always written, acceleration is always written as meters per second. I don't need that yet, I'm only using velocity. So if I have something that's moving at 1 meter per second, all right, I know that it's, and we're going to say it moves at 1 meter per second for 3 meters. All right? I can figure out how much distance it covers simply by multiplying the meters times the seconds. All right? So if it's going 1 meter, all right, every second times 3 seconds, that's going to tell me that it went 3 meters. That is actually the same as the area under this parallelogram. Now, at the end of 3 seconds, let's say it accelerates for 10 seconds, all right? It undergoes constant acceleration. And in 10 seconds, let's say it increases, has a constant acceleration of 1 meter per second. So at the end of 2 seconds, its acceleration, its factor is going to be going at 2 meters per second. At 3 seconds, it's going to be going at 3 meters per second. At 4 seconds, actually, it's going to be going now. In 4 seconds, it's going to be at 5 meters per second. 6 seconds, 7 seconds, 8 seconds, 9 seconds, 10 seconds. All right? And I know 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Almost got it right. Okay, almost got it right. Got close. All right? Now, there's some pretty cool things I can do with this because geometry works. All right? I can actually tell by continuing this line out and creating a right triangle how much area or how much distance was covered by that vehicle, by that accelerating vehicle. All right? All I have to do is know that the area under a rectangle is the length times the width, right? So my area under this rectangle right here is going to be 10 because we said it's accelerating for 10 seconds. And it was going to increase at 1 meter per second. All right, so I know that this area is 10 seconds. It is 10 seconds, and I know that it started, my initial here was 1 meter per second. All right, so I know that this area is 10 meters. All right, therefore I also know that the distance it covered was 10 meters plus this triangle. Now the area of a triangle is what? 1/2 base times height, right? So what is my base here? I know my base is 10, right? My height is also going to be 10, isn't it? Okay, it should be 10 because it's increasing 1 meter per second. 1, 2, 3, 4, 5, 6, 7, 8, Now I'm 10. All right, accelerated for 10 seconds. So I know that my height of this is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right? So, 1/2 10 times 10. That's going to be the same thing as 1/2 times 10 times 10. All right? 100 over 2 is going to be 50, right? So I know that the area of this triangle is 50. So the distance I covered from the point of acceleration is going to be 60 meters. You what? Question? What? Got it? Yes? You with me? Yes or no? All right. So, I know that my distance covered here is going to be 60 meters. All right? It's going to be my 60 meters right here. That's how far it's going to cover. All right? I can do the total for this because I know I moved, in the first one I moved 10 meters per second for 3 seconds. So I know that this area is 30. Okay, or sorry, this area is 3. I can add that in, and I know that I've gone 63 meters. All right? Cool little things you can do with triangles and such. All right? You can do the same thing with acceleration in the opposite direction. Okay, if we slow down over a period of time, and it's the same as we looked at before, if we have our 60 miles per hour and we decelerate to 0 miles per hour, all right, and I do that in 3 seconds, we can put that into a graph. My velocity is up here, all right. 20, 40, 60, 1, 2, 3. Now, the slope of my angle is going to be down now, right? So my acceleration is going to be a negative. My acceleration is going to be negative every time. So if this is 60, okay, times 3, over 3, sorry, 1/2 base times height. Base times height times 20, 1/2 that. 60, we know we can tell exactly how far we went, exactly how far we traveled. Any questions? That's just future, that's stuff we're going to be doing later on. I wanted to throw it at you. All right, I'm going to give you some time now to work on your study guides. I would make sure that I wrote everything I could. If there's something in there, I'd write everything I could about it. All right, because that's the only thing I'm going to let you use. No more notebooks, and I'm going to lock the Chromebook. Yes? Yes. That's normal force. All right, these are also parallel force. The gravity and the normal force, they're parallel forces because they're what? They're on the same plane.
So I can write that for this.
All right, what are parallel forces? Yeah, that would be a good diagram. Okay? But you have to remember that they are in the same plane. It doesn't matter if they're horizontal, vertical, diagonal, whatever. Anytime you have parallel forces, they're on the same plane.
I'm not lying.
So, as you have drawn there with your normal force,
Do you have any,
all right?
good. Do you have anything for the pencil?
Gravity and the normal force are parallel forces. All right? Something pushing from this side and something pushing from this side, those are parallel forces. If all of a sudden I get a push from this side and a push from this side, they're on the same plane, they're a parallel force. All right?
So they're all
Parallel forces can just be added. Don't have to don't even have to multiply. Just add them up. Just add them up. 1, 2, 3, 4. 4 plus 2 are 6. 6 plus 2 are 8.
Dude, I really need a pencil. Get one. That's why I'm asking you for one. Oh. I know you have more than one pencil. Yeah, for me. That's 9. Give me a pencil.
Did you get this one?
Yeah. Yeah, it's nothing.
It's not. You got pencil already?
Does everybody have a study guide? Anybody need one? Questions on your study guide? Anybody got any questions about the study guide?
Alright, also, number 4, are you saying?
There's no numbers. Don't put numbers on them for a reason.
Are you saying this? Is that,
All right, what do we call? What can we use when forces are not parallel? What's that called? Right, that's the rule of the parallelogram rule, right? All right. What mathematical concept can we use to find the force mentioned? What do we call that? Okay, what is that called? Starts with a P. Greek philosopher and mathematician.
Yeah, I know it's that,
It's not Plato.
I know, what is it called?
Do you have it written down?
Oh, it's good. Are you talking about it's good? Yeah. Yeah, that is.
Or you could have just write down a squared plus b squared equals c squared.
Okay.
But yeah, I'd know the name of it.
Yeah. This is it. Okay.
Average acceleration will also equal the slope of the line. And we'll get to that later. That's not on this test. On the next test. But it'll help you with this test, you know all that stuff. It'll actually make some of the stuff easier. Where's your parallel? Get used to drawing diagrams. Get used to drawing, that's, get used to drawing diagrams. It's correct, yes.
Oh, yeah.
But get used to drawing diagrams. Because after this test, we're going to start adding the math components in as well. And you're going to have to show your work. And showing your work is going to be more important than getting the right answer. The right answer is not going to be hard. Y'all line up the door. Go back.
I don't like this.
Grab them cookies.
Then I bet you won't put some on your, no. Why not?
Wow. You should have took it.
Somebody wanted it.
I don't like it very much.
Then why not?
Would you get on the course in Altair Street? Wow. That's so good.
What grade went out to?
My grade, I had an A in that class and now I have a C.
You're an A?
Yes.
Make sure you have your study guide when you come in tomorrow. Make sure you're, like I said, you can use it if it's written in your own handwriting. No copying and printing like y'all cheated last time. Everybody turned in the same one. Yes, you did.
I don't know.
I didn't know.
Some of y'all, y'all didn't even bother to change the font. Same picture. Caleb, don't line up at the door. So make sure you get those finished. Tomorrow, I'm not going to give you all the answers on it, but we'll go over what you need to know. All right, and you're not going to have time to write everything down. I'm not going to slow down so you can write all the answers down. So make sure you have it done so you can check your answers. It'll take a little while. There's a lot of information on there. A lot of stuff. And then the test is Monday. Y'all are by far my quietest class. Y'all are the quietest class I have. Y'all are just quiet.
We're good students.
I don't know about that.
We pay attention in class.
Y'all are my quiet class. X class is my loud class.
We're the best.
Is that a good thing or a bad thing?
Sometimes it's good when they're on task.
Sorry.
So this good.
When they're poking each other and pinching each other, it's a bad thing.
Yeah.
I know that.
That's all I do is walk towards you.
We're trying to cheat for.
This.
I want like this.
I'm just saying, homecoming is coming up.
That's fun. You can go and move back.
I don't think I'm
Y'all have a nice day. Stay out of trouble. Don't do anything stupid.
One's a natural one. The other one is.
No, but for real.
I'm tired as you know what, man.
It's Thursday, man. Not much more to go. I gotta redo your test. So
Looks like 20.
Need some coffee.
crap.
That one.
I love this song. Shut the fuck up.
Babe, can you grab the square?
No. No.
Yes.
No. Just put it on my. Put it right here. Oh my. He be drenching this. I'm gonna get blown. No! Get off. Yo, why don't you guys check your season?
Oh, I just relaxed.
Hey, yeah.
There you go. Yeah.
Get out my business. Get out my business.
Yes.
Hey, Ari. Ari, hey. Hey, Ari. Hey, boo. Hey. I know what I like. I didn't take the nap.
You said 5, 6, 7, 8.
Ari, carry my book bag.
Slow down in the same direction.
Journey, one for number 2. You gotta stop. What's the name of
Slow down.
Slow down.
Slow down like Alex. Yeah, slow down.
Oh my God. Oh, she said.
Stick a drop in there right here. On the Evo camera.
Man, always.
On the Evo.
On the cake, I tried but the angel took the side, lead me to.
What's up, kids?
I love you. They told me to slow it down.
Yeah. All right. Who's missing? Who's missing? Who's missing?
Everybody here. Wait, no.
Yeah.
So,
Yeah. On me. I said it made my ears hurt. And it was like, what do you think the song was about? I was like, that some people just have people opinion.
Already that's it.
Whatever. She said she's mad at you. She said she's mad at you.
about life.
Oh, right. That's good. Penn, Sinclair, Connor, Cole,
Gary.
Kevin,
Ari.
Reed, Jesse,
Here.
Wade up there, Ariana, Caitlin, College, you up there?
Yes.
Nugent, here, Carson, here, home, Solo, up there, Albert,
Here.
there, and here.
It's like
All right. All right, so let's kind of pick up where we left off. Yesterday was kind of a diversion for a little bit. Okay, just kind of moved and started to work on something else, and now let's get back into our thing. All right. All right. Now, we've talked about this before, but it bears repeating. Velocity and speed are not the same thing. velocity is a vector, therefore it has a direction, right?
Didn't have a specific direction.
Therefore, it must have a direction. So anytime we do a velocity graph or a velocity problem, we need to know where it's going. Speed is the absolute value of velocity. Anytime we have constant velocity, it implies a constant direction, therefore a straight line. All right? And I'll come back and write that up here in a minute. Let's go back to our touchdown example yesterday. All right? So, Sincere picks up a fumble. All right? Sincere picks up the fumble. He starts running. He picks it up on the 1 yard line. He picks up a fumble. And he runs over a guy here, and he runs over here real fast, and then he jukes out a guy right here, and then he runs over the quarterback right there, and then he's running towards the goal line, and a bunch of guys jump on his back, and he's all of a sudden he's going real slow, but he just keeps moving forward, moving forward, moving forward, moving forward, moving forward, and he crosses the goal line and returns a touchdown, 99 yards. Fumble. All right.
Can you run that again, Joe?
5 guys on his back. Just totes them in the end zone. All right. Now, if we were to look at this as a vector, as a velocity, the only thing we would be interested in, all right, would be how long it took him to get from that point to this point. All right. That would be the vector to the goal line. All right? All of this other motion in here implies something else. And we'll talk about what that is in a minute. But right here would be his vector to the goal line. So we would just measure it in that distance. How long did it take to get from 1 yard all the way down to the goal line 99 yards away? All right? And he just ran, just stomping on people, running over folks, returned the fumble 99 yards. All right? We can figure out his average velocity there. All right? His velocity probably would not be constant. All right? Velocity would probably not be constant. And if we had somebody with a stopwatch at every 10 yards along the way, or every 9 yards along the way, we could see that his velocity wouldn't be constant. All right? But we could get his average velocity by how long it took him to go from point A to point B. So, our formula here for average velocity, right? Average velocity is equal to change in velocity. Sorry. sorry, change in displacement over change in time. Because remember, displacement is a vector quantity. All right? And we can also write that as change in displacement over change in time. Which means, right, position final minus position initial over time final minus time initial. All right? That all means the same thing. All of that means the same exact thing. So we can find that average velocity. We can also have constant velocity. All right? We would do average velocity for things. Average velocities are really good to look at for weather. All right? They will take, if you're looking at a storm system, you can look at a storm system and they will look at the velocities of winds at certain elevations, and winds at the ground may be moving different from the winds high up in the storm. That's one of the ways they find tornadoes. They use Doppler radar and they can tell if it's green shifted or red shifted, okay, by which direction the wind is moving, and it's actually reflecting off of the things that are being blown around by the wind. All right? Like the Weather Channel is what I watch at night, because there's nothing else on TV that's worth watching. I do watch The Walking Dead. But I watch The Walking Dead because they literally filmed it in my backyard in Noonan. Yeah. We didn't know what they were doing. And when the first season came out, it was literally filmed in my backyard.
I should have known.
Well, we walked back through the woods. Me and the boys walked back through the woods and looked, and we were like, they're filming something over there. They yelled at us, hey, get out of the shot, get out of the shot. We were like, okay. And, but yeah, they literally, the first season was filmed in my backyard in Noonan. And I met all those guys too. Like the star, the guy that plays Rick, Lincoln, can't think of his name. He's like 5'4". Seriously. Guys, maybe he's 5'4" at most.
I'm taller than him.
You taller than him. You are taller than him. Little bitty dude. Little bitty guy. And he's a little short dude. And then like the guy that plays Daryl, Norman Reedus, he's about 6 feet tall. The guy that plays Negan, he's a little big guy too. It's funny because you know they make them look so big on camera. They ain't. They use angles and stuff. Matter of fact, they have to shoot Rick at different angles when he's on camera with when he plays Carol, because she's like 4 inches taller than him. She's like 5'8". She's one of the tallest ones on scene. It's pretty funny. Anyway, I met all those guys. One guy, I got mistaken for Negan one time when I was in a restaurant because I was all scruffy and it was like dark, and some kids came up and said, I don't know the guy's name. Are you so and so? I should have said yes. Yeah, you want an autograph? But whatever. Anyway, nothing good on TV, so I watch Weather Channel. Well, on the Weather Channel, and when you're following weather, what you'll find out is they need to know these velocity vectors in order to tell where the storms go. All right, and if they know what the vectors are, they can say, well, this storm should arrive in Columbus in 45 minutes. All right, even though the storm may be a shorter distance away, and the storm may actually be moving at a greater speed because of winds aloft and winds underneath, and mid-level winds may be changing it, because those are all forces that affect how fast the storm's moving. Storms don't just have winds going in one straight line. All right? They bounce off of stuff, they move around, and that's why one of the reasons you get all the tornadoes, you know, just from north of here up to about Carrollton, is because the wind all of a sudden has to go up off the fall line. It's compressed up, it speeds up, and that's why you get all those tornadoes in there. Same thing with just south of here, down around between about Eufaula and what's that? Dothan's in the middle, and there's that little town in Florida. There's actually a little rise in elevation there when storms come in out of the Gulf, and that air gets pressed up. That's why you get all those tornadoes down there. Okay, so the topography matters, and that changes wind vectors. Okay, when those winds get to moving around, they get compressed. They know how much elevation is in there. Forces are now moving faster than they were before. That's something we'll learn about when we talk about hydrodynamics and fluid dynamics. And all of a sudden, more air is moving at a same rate but a different velocity. It starts spinning and causes storms. These are really important for things in storms. Okay, so other than average velocity, we also have to be able to understand constant velocity and what constant velocity implies. Constant velocity implies movement at a uniform or constant speed in a uniform direction. Right? So when we've got something that's moving along at a constant speed in a constant direction, we know we've got constant velocity. Very few things in nature that we see have constant velocity. But we do need to know what constant velocities are. These become really important for things like space travel. We have to know constant velocities for space travel. Like I told y'all yesterday, there's no reason for the engineer in Star Trek to be screaming up to the captain that the engines can't take anymore to keep up this speed. Why? There's no gravity, and there's nothing in space to slow them down. Just shut them down. You'll keep going the same speed. All right? You're just going to keep going the same speed. There's nothing to slow you down. That would be constant velocity. All right? In space, you can get that constant velocity. So it's really important for space travel. If I throw a ball up in the air, it tends to fall back down to Earth. If I hit a golf ball, it's going to go everywhere except for where I was trying to hit it. All right? But it's eventually going to come to rest. That means it's going to have a change, okay? Anytime we have a change in velocity, that is called acceleration. Right? There are three ways things can accelerate. right? First one's the most obvious. Change in speed or change in speed in the same direction. So I got a fast car. 1965 AC Cobra 427, ram air hood, 2.4 barrels. Dual straight exhaust. It'll fly. Fastest production car ever made up until that point. And it will go from 0 miles an hour to 60 miles per hour in 3 seconds.
Wow.
Actually, I think it's like 3.12 or something. All right. It's fast. A lot of power. All right, so I'm changing speed in the same direction. So I have to have a direction. And we can name that direction whatever we want to. All right, we can name that direction down the track. We can name that direction to the goal line. We can name that direction east, west, to the right, to the left, north, south, up, down, whatever we want to name it. But as long as it is in the same direction. All right? It's got to be in the same direction. So in this case, I'm changing speed from 0 miles an hour to 60 miles an hour in 3 seconds. Well, what does that look like on a velocity diagram or a velocity velocity formula? Well, our formula for velocity, change in velocity, is change in velocity. Should I do this now? No, I shouldn't. Okay, but we'll come back to that. But just for the sake of kind of seeing this, y'all don't have to write any of this down. All it is I would do the same thing as I did before. Okay, my change in velocity over my change in time. Okay, that's going to equal velocity final minus velocity initial over time final minus time initial. All right, and that's going to equal 60 minus 0 over 3 minus 0. That's going to give me 60. And again, I need to miles per hour, 3 seconds, 60 miles per hour over 3 seconds. And that's going to give me what? 20
miles per hour per second.
Good. 20 miles per hour per second. All right?
Nice.
Very good. Glad you got that right. That would be my acceleration rate. That means that if I was looking at my speedometer, like I said, this isn't important. Y'all don't need to write this down right now. I would be going at 0, 20, 40, 60. I would increase 20 miles an hour over each second. Now, acceleration is never that smooth. All right? It would actually probably be a parabola, and it would continue to increase over the next amount of time until it got up to about 210 miles an hour. But yeah, there's a lot of engine in a little bitty car. All right, Carroll Shelby invented this thing. It was awesome. Anyway, it wouldn't be that smooth, but that would be my average acceleration. All right, that's increasing acceleration. All right, so I change speed in the same direction. All right, so in this case, I have a vector quantity because acceleration is a vector, 20 miles per hour per second to the east, or whatever I want to say, down the track. All right? So I'm going to have everything there. All right? By with me so far. So I can change in speed by increasing my velocity, all right, in the same direction, or increasing my speed in the same direction, which is velocity. Number 2, all right? Number 2, I can slow down. And I should have said speed up. Speed up. Erase all that, just right. Speed up in the same direction. I can slow down in the same direction. So let's say I'm going 20 miles an hour, all right? Or say I'm going 60 miles an hour. I'm going 60 miles per hour. And a deer jumps out in front of me, and I go from 60 miles an hour to 0 miles per hour in 2 seconds. That's some serious braking power. All right? I slam on the brakes, and it brings me back down to 0 in 2 seconds. I don't know that you can do that. But we're hypothetically speaking here. So, same thing, I use the same formula. So I need my change in velocity over my change in time. All right? My change in velocity, remember, is velocity initial, velocity final minus velocity initial over time final minus time initial. All right? So my final velocity in this case is what? 0. All right? My initial velocity is 60 miles per hour. All right? My time difference, all right, is 3 minus 0. Okay, seconds. All right? And that's going to equal 0 minus 60 is what? Negative 60. And sorry, this was 2, wasn't it? Over 2 seconds. That's miles per hour. All right? I divide it out and I get what?
Negative 30.
Negative 30 miles per hour per second. All right? This will look very different on a graph. So now I've got negative acceleration. Okay, this is negative acceleration. And again, it would have to be in the same line. I would have to say to the east or to the north, south, up, down, sideways, down the road, you know, towards the corner store, whatever. All right, I just have to give it a direction. All right? So as long as I'm moving, slowing that in that direction. Okay? To the east. I think that's the way we were moving before. And we can designate direction whatever we want it to be. We can designate our positive and negative direction whatever we want. It always helps if you keep right positive, left negative, just because that's the way it is on your graph. Or positive up, negative down, helps on your graph. Okay, you don't have to sit around and figure out, okay, which it was going, my positive, if I make my positive direction to the left, all of a sudden I'm having to flip it around the graph. All right? So I slow down in the same direction, just like before. All right? Now, the other thing we can do that is a change in velocity is change in direction. I don't even have to change speeds. If I change my direction, I am accelerating. Because I'm no longer moving in the same way. So if we look back and think about our touchdown, okay, Solo just ran. He changed direction a bunch of times. All of those changes in direction are acceleration. All right? They are all acceleration. Any change in direction is acceleration, even if speed does not change. All right? We go out to Talladega. We're going to watch some race. Y'all watch race? Watch race. I'm old school. I was going to NASCAR races when they were long time ago, before they had any rules. Just about. Everybody cheated. I saw Richard Petty, Cale Yarborough, David Pearson. I saw all the old guys. Okay? Let's think about Talladega. You don't slow down. They don't lift out of the corners unless somebody's in the way. They just put the hammer down, keep it gassing, and go. Because it's huge. They don't have to come out of the accelerator. Okay, unless there's something going on. So they're going the same speed in the corners just about as they're going in the straightaway. Difference is their velocity changes because the direction changes. All right? It's an enormous, wide, looping track. And it's a trioval. It's got these great big turns in it. And when they're on fresh tires, they can just go. All right? So when they're coming out of these straightaways, especially along the front turn, their speed doesn't change very much as they go around. But the velocity does, because the direction is changing. And we call this angular momentum. They may be going straight here, but as soon as they get into the turn and start turning that car around, velocity changes because it is a change in direction. All right, they are no longer going to the east. All right, and it is a constant vector problem, and they have all kinds of cool stuff that they use to figure out just how fast they can keep that car going around that turn without letting it slide. Because when you slide, you wear the tires down. Right? You lose momentum to friction. We'll talk about what all that is later. All right? Speed may be the same, but velocity is different. For example, I can swing this at a constant speed. Don't get hypnotized. You're a chicken. No, don't get hypnotized. All right? Mullins laughed. He thought it was funny. I could tell. All right? But it's constant speed. But it is not a constant velocity, because it is always changing directions. There is a force involved besides me slinging it around. There's a force involved that is keeping it moving in a circle. That force is supplied, all right, by the little lanyard here. And there's a normal force right here that keeps it from flying off, okay? There's a support force that keeps it from flying off. If it were to release, it would go in a straight line in whatever direction it was going when the lanyard broke or when I let go of it. Ooh. All right? But as far as we can look at right now, it is just moving in a nice circle. All right? That is constant acceleration. It is constantly accelerating because there is a constant change in direction. All right? Not speed. The speed, we can judge the speed. All right? The velocity is not the same though. And we can figure it out. We can figure out what the radius is. Okay? Figure out what the radius is, and we can tell what speed the end of it's moving at out here. All right? We can figure out the speed. Once we know the speed, we can figure out the angular momentum, and therefore the angular momentum will give us our velocity vectors. All right? But it's constantly changing. Therefore, okay, it's constantly accelerating. So anytime something is moving in a circle, all right, there's really no such thing as centrifugal force. It's acceleration. All right, it's angular momentum, is what we call it. All right, so changing three ways things can accelerate. All right, changing velocity is acceleration. Three ways. It can speed up in the same direction, it can slow down in the same direction, or it can have a change in direction. All of those things are acceleration, right? Whether it's something speeding up or slowing down. Now, you may ask, where's deceleration, Coach? There is no deceleration. We don't use that term in physics. It's all acceleration. It's either positive acceleration or negative acceleration. And we'll see that when we put it on a graph. When we talk about acceleration that is slowing down in the same direction, the graph will slope differently than if it is speeding up. All right? When we speed something up, the graph is going to go up and to the right. When we speed something down, it is going to go down from left to right. All right? The slope will be different. Now, our speed is going to be our change, all right? Our absolute value of our velocity. All right? Questions? Acceleration. Okay. A change in velocity. All right. Average acceleration. A change in velocity divided by our change in time. That is the same thing as saying change in velocity over change in time. All right? And that is our velocity final minus velocity initial over time final minus time initial. All right? That's how we're going to get our average velocity. Constant velocity is easy. All right? Questions about changes in velocity or what acceleration is. All right, y'all get to work. Y'all got some time right now to work on your study guides. All right? Make sure you hand write them. I will not accept a printer copy. All right? You can only use a handwritten copy on the test. If I catch you using one that's been printed off of a computer or that you answered as a Google Doc, I will take it from you and give you 0 credit. All right? So it's got to be handwritten. Yes? Yes. Take a couple minutes right now. Finish up on those study guides. Make sure you have it completed before tomorrow when you come in. I'm going to go over it, but you're not going to have time to sit there and write the answers down. Because there's a lot of stuff in there. But I do want to give you the opportunity to check your answers. If you got questions, now's the time to ask them. Alright, y'all grab your stuff up, go get your bags, and we go ahead and spray.
Here.
Look up before I spray you down.
All the stuff is down. You can walk with it. Oh,
Spray down.
and I hope your phone's yeah, like you know when Caleb said.
Don't line up the door to make sure.
You need to change it.
I'll start giving you all the work to do.
Freeze. Y'all play. I'm gonna really get an AM94 and just go crazy. You know what I mean? Y'all know that.
It's a gun in Call of Duty.
Chill. It's not a gun.
It's not a real life gun.
What type of gun?
It's an assault rifle.
Alright.
It's like an AK knockoff.
We know it's an AK with
It's
no
a
recoil.
variant of the AK-47 modernized.
What is
It's like an AK-47. It's very modern looking and then skeletonized. I don't care. Skeletonized guns are cool. They always are. So beautiful.
Also would die.
I'm scared of my cousin.
Also would die.
Whenever he's angry, he always takes out his aggression on other people in Call of Duty. One day I just feel like he won't go to the game.
Also would die, bro.
It just scares me. Because he'll like start yelling. He'll start yelling into the mic and saying, "Die, die, die."
My man died. He cut Buddy head off.
Favorite thing I've got that I just love is my little kill pick. 9mm. That is the most.
You did your
It's better than 22. It doesn't jam up as much as far as just going out. It's got an 18-inch barrel, so it's got about 110 yard average. Put a scope on it. This thing got hit at 110 yards.
Ain't no way.
It's a fun thing to have. It's be automatic.
That was me.
Huh?
That was me. You know about you.
I promise you it is. You want to see?
That's trouble. Don't do anything stupid.
I don't know. I told her not to talk to her.
Well, I can't say no because somebody almost fell in the trap too.
Alright. You know what? That's something.
You know it's true. So you know my alarm.
Still sitting back there?
Huh?
Still sitting back there?
Yeah, I don't want
I'm getting worse.
I need Austin not to today. Like, not.
sure I'm getting any better. I need to change the way I practice.
Dimmer in here. Because his lights aren't all the way on.
You think keep popping up. Tomorrow. No.
What are we doing? We need our book, Caitlin. We have to go get our book.
Are they running?
So I've seen her get something. I don't have my book here. Figure out
Really?
No, it's the principal.
I'm not gonna let her win.
I got strike from her.
I know you want to next to me.
I could grab something on
Dad, why don't you just put it right there?
That's for you.
I didn't see that. I'm not dealing with these.
Please excuse interruption. At this time, students that have signed on through Naviance for our Mercy University visit, please head down to the media center. Stop by the high school office for your pass. Only those that have signed on to Naviance.
No, not right now. No, it didn't happen like. I heard about it now, but I'm sorry. I heard
Oh, you have a whole boyfriend?
Bring on Carlos, bro. More Carlos. More Carlos.
Stop wiping off kids.
What's up, kids?
Today, how about the one time?
What?
No. You get one little bit of toe for the whole thing.
I'm like one side down in my car.
Yes, I'm like my toe.
That's so embarrassing for her.
All right. Who's here? Who's not here?
I think everyone.
What? Right here.
Whose bender is that?
Oh.
Where they don't need to be called.
Who's this specifically causing these
I
problems?
don't know, we'll find out.
What do you
Cause.
And Natalie.
Whose binder is that?
do?
Natalie, is that your binder?
All right, let's see. Natalie. Dan's here, Jordan's here, Isaiah. Online, Thomas is there. Stephen's online. Caleb, Barry.
You never know your wife, but that's okay.
Where's Caleb?
You right here?
Oh, there he is. All right, let's see. Carolyn.
Here.
Austin's here. Morgan.
Hi. Yeah.
Claire's here. Let's see. I'll call us David. What's up, kids?
Coach. All right.
This is Monday. Remember, you can use your study guide. However, you'll have to have it handwritten. If it is not handwritten, I will take it from you and give you a 0 on the assignment. Okay? So study guides have to be handwritten. Right? Let's see. Where did we leave off? All right. Remember this, velocity and speed are not the same thing. If you've already got that written down, then you're good. Velocity and speed are not the same thing. All right, velocity and speed are not the same thing.
That's correct.
Velocity is a vector. Therefore, it implies direction, implies speed or movement. Let's say movement in the same direction. Okay, so anytime we're talking about velocity, we're talking about movement in the same direction. That is implied. All right? Speed is the magnitude of velocity. It can also be expressed as the absolute value of velocity if we have a negative number. All right, because we can't have negative velocity if it is moving away from what we decide is the positive. All right, so if I'm talking about the positive is east and is moving west, it has a negative velocity value. But its speed value will just be the absolute value of that velocity.
Coach, is that where it says speed is that magnitude?
Yes.
Coach, can you move, please?
Yeah.
Thank you.
Now, from there, let's talk about kind of what we talked about yesterday, the touchdown. The touchdown run. All right? Because velocity is a vector, therefore implies direction. All right? Pick up a fumble. Got here, kickoff comes. Kickoff, and who's our kickoff returner? Catch the ball in 1 yard line. All right? He starts up the field, he goes over here to the right, and he goes through traffic, he runs over here, jukes this guy out of his shoes, runs over the kicker, and runs touchdown. All right? So there's a lot of movement, there's a lot of distance, there's a lot of things that we can say. Now, if we were going to make this a velocity problem, all we would want to know is the vector between point A, point B, and therefore a straight line. All right? That is what I would have. All right? So my velocity and my speed would be two different things. My average velocity and my average speed. Now, if I just did my average speed over the same distance, it would be the same. But my average velocity here would not take into account all of these twists and turns. He may actually be running faster here than he is here. All right? Maybe running faster here than he was at the end. But on an average, okay, we're just talking about one direction. All right? So here we have one direction, one dimension. All right? For our vector, and that would be to the goal line. So my velocity will be how long it took to go from point A to point B. All right? And we would divide that by the time. So my value here is, okay, my displacement, change in displacement, over my change in time. All right? And change in displacement equals position final minus position initial over time final minus time, keep making those X's, time initial, all right? And we can plug in the values, all right? So this is for velocity. All I need is my initial position and my final position. All those positions in between are just part of the average. Right? They just go in there. They're implied into the formula. All right? So constant velocity implies constant direction. Oh, man. All right. Now, we don't run into this very often. Not within the Earth's gravitational field without forces being implied or imparted onto an object. Right? We don't run into a lot of constant velocity. Now, out in space, we'll run into constant velocity. Like I told y'all yesterday, when the engineer on the Star Trek Enterprise was screaming at the captain, he couldn't keep the engines going to keep up that speed, that velocity through space. Captain should have just called down and said, shut them all down. We'll keep going. That's how space works. All right? There is no outside force. There is no gravity. There is no friction. There's no outside force. If you're already going along at warp 6, you're going to keep going at warp 6. There's nothing to slow you down. All right? Nothing there. Just going to keep zipping. Keep going. All right, so we have that constant velocity. We'll get that in space. That doesn't happen very often on Earth. All right? We get it, if we continue to power something, yes, we can get some constant velocity, but it's not something that we have a whole lot of. All right? Average velocity, obviously, I gave you the formula for earlier.
Velocity.
Sorry, I've been teaching this so long today, I'm like, my brain's gone.
So
Do what?
For constant velocity, it has to be at equilibrium.
Yes, constant velocity is going to imply equilibrium.
Okay.
All right. Now, all right, change in velocity. Anytime we have a change in velocity, that is called acceleration. All right, that is anytime we have a change in velocity. There's 3 ways we can have acceleration. All right? 3 ways to accelerate. All right? Number 1, speed up in the same direction. Let's just say increase speed. In the same direction. So,
Is that an EA increase?
do what?
Increase.
Increase. You know how to spell it. All right? I didn't see all you there. Let's see. All right. So, an increase in speed in the same direction. All right, Coach Anderson wants a fast car. So, I go out and I buy a 1965 AC Cobra with 427, 2 4-barrels, dual straight exhaust. It is loud, it is low, and it is fast. All right? One of the fastest production cars ever made. All right? If you've ever seen the movie, what's that movie called? Shelby? That's what it was about. Shelby AC Cobra. Right? Now, Carroll Shelby invented it. I can increase speed in the same direction. So I get my AC Cobra. I go out and I go from 0 miles per hour to 60 miles per hour in
3 seconds.
3 seconds. All right? Now I can stuff that into my acceleration formula. All right, now my acceleration formula is going to look just like my velocity formula. All right, and this is one of those things that you kind of got to get used to. All right, so my acceleration formula is the change in velocity divided by the change in time. And that's going to mean that is my velocity final minus my velocity initial over time final minus time initial. All right? And that's going to equal 60 minus 0, 60 miles per hour, I should say, over 0 miles per hour over 3 seconds minus 0 seconds, my starting time. That's going to give me 60 over 30 over 3, and that is going to give me how many miles per hour?
20.
Sorry, miles per hour, and that's seconds. So that is going to be 20
miles per second.
Miles per hour per second. All right? So that's going to be the rate I'm accelerating at. What that tells me is if I look at my speedometer and I look on there and it's got a 20 and how fast that says going? It's got a 20 and a 40 and a 60. All right, 0 over here. In 1 second, if my acceleration is constant and uniform, I'm going to be going 20 miles an hour. In 2 seconds, I'm going to be going 40 miles an hour. In 3 seconds, I'm going to be going 60 miles an hour. Now, this would not be the speedometer for AC Cobra. Okay, it goes up to 200, I'm sure. All right, the top speed on this thing was around 210 miles an hour. It was a massive engine on a little tiny body. All right, so, but each second I would increase by 20 miles an hour. If I continued that for 4 seconds, how fast should I be going? 80. I'd be going 80 miles an hour. Now, here's the thing. This always works out to a parabola. It is very rarely smooth. Okay? It may smooth out over time, but most of the time it's going to make a curve, and we'll worry about that later. Right now we're going to talk about constant acceleration. All right? So the first way I can accelerate is to increase speed in the same direction. All right? Second way to accelerate. Decrease speed in the same direction. So once again, my velocity is changing. A deer jumps out in front of me. I'm going 60 miles per hour. Right? I slow my car down. I accelerate to 0 miles per hour. And I do that in 4 seconds. We'll make it. All right? So I can use the same formula here for average acceleration. Okay? Change in velocity over change in time. Okay? Equals velocity final minus velocity initial over time final minus time initial. All right? And then I can plug my values in. My final velocity is 0 minus 60, 0 miles per hour. And my initial is 60 miles per hour over 3 seconds minus 0 seconds. And I get negative 60 now over 3. All right? And therefore my acceleration is what?
Negative 20.
Negative 20 wait a minute, I said 4, didn't I? I said 4 up here, so I, look at there.
15.
Okay, 4 seconds, or 4 seconds, and now it is
Negative 15 miles
negative 15 miles per hour per second. All right? Yes.
Can I go to the restroom?
Yeah. Now, and here's the thing, and stick this in the back of your head. In physics, there's no such thing as deceleration. All right? We can have negative acceleration. All right? We can have negative acceleration, but we can't have we don't say the word deceleration. It's always acceleration. All right? Whether I'm speeding up or slowing down. And it's always in the same direction if I'm talking about speed. Now, there is a third way to accelerate. All right? Racer. There we go. Because velocity implies direction. I am also accelerating when I have a change in direction. Even if I'm moving the same speed. So even if I'm moving the same speed and I change direction, I am accelerating. I might initially be accelerating to the north, and then all of a sudden, because I'm such an awesome athlete, I can put my foot in the ground and keep running at the same speed to the west. I am now accelerating to the west. I have changed my acceleration. All right, I have changed my velocity. Okay, so anytime I change the direction of my velocity, I'm accelerating. If we look at Talladega, y'all watch races? Y'all watch NASCAR?
No, it's too slow. What? You said NASCAR is too slow? They got like 1,200 laps.
I'm like an old. I was around NASCAR when Richard Petty. All right, Talladega is a big what we call tri-oval track. It's enormous. It's over 2 miles around. All right. Now they come down this straightaway at 200 miles an hour. Now here's the thing. Talladega is so big, they don't slow down. They don't ever come off the accelerator. They put the hammer down and they just keep going. That's why these great big tracks, what they call restrictor plate tracks, where everybody has to have the same pretty much fuel injection system going in. They used to call them restrictor plates. They were getting so fast, they made them change the rules. So they put this in there. Now, they don't slow down anymore. They come off this going 200 miles an hour, and then they go into this turn, they don't even come off of it. The thing is, their speed doesn't change, but their direction does. Therefore, they are now accelerating, all right, as their direction changes, all right? So now they are accelerating around the curve, and that is what we call angular momentum, and we'll get into that later. But here's a way to think about it. All right, I have keys on a chain, right? Now I can swing these keys and make them go at a constant speed. All right, they have a nice. I can make them go. If I gotta get them going, I got to give them a little more energy on the way up. But I can get them going at a constant speed. Now, even though their speed is constant, their velocity is not. The reason the velocity is not is because the direction is constantly changing. There has to be a force on it, therefore, making the direction change. The force is imparted by the lanyard. All right? And since the lanyard has a pull force, all right, that is essentially the same as a normal force here on the key ring, it keeps it changing directions. Yes, ma'am. Yes, you may. All right? It is constantly changing directions. Well, shoot. No Trail of Tear duels this year, guys.
No what?
The dual tournament we went to at Russell County, they canceled. All right. So we'll have to find another tournament. All right. But change in direction is acceleration, even if I'm going the same speed. Same speed, and we could average out the speed, but this is constantly changing velocities. Because velocity implies what? Movement in a straight line. All right? That only happens in outer space. We don't see that much on Earth. And we have some things that do have some fairly constant velocities. And we measure those velocities, and we don't want to know what they are. Things like storms. If y'all ever watch Weather Channel? You ever watch the Weather Channel? That's how they track storms. This is what they use when they track storms. They use these wind velocities, all right, to try to determine what direction the storm is going to end up and how long it's going to take it to get there. Because the velocities of a wind way up in the atmosphere may be different from the mid-atmosphere, may be different from the lower atmosphere. That's one of the ways they find tornadoes using Doppler radar. They figure out if the rain is moving towards the radar or away from the radar. And if they can tell the rain or debris is moving toward a center of rotation and away from a center of rotation, they're able to see that because of the blue and red shift that you have a tornado. And those are things that happen when you have changing velocities. All right, constantly changing velocities of a tornado. It's going through angular momentum. All right, which is a constant change. And we'll get into what all that means later. We'll do the formulas for changing velocity going around a circle. All right, what happens with a pendulum. All right, that all matters how that works out, especially when we start talking about, like I said, storm chasing. Those guys that go out and get in a van and they chase tornadoes down, they're looking at winds aloft, they're looking at mid-level winds, they're looking at low-level winds to try to give themselves the best position to be able to get good pictures of a tornado. Or they're trying to put themselves in position to put out instruments to try to measure winds inside of a tornado or pressures inside of a tornado. And a group recently came within seconds of a tornado, and they just about got smashed because they didn't realize how close they were, and the winds had changed because it takes instrumentation time to figure out those vectors. Has to go through a computer program, and by the time they got out of the way, it was just in the nick of time. And the place they were in was just, the place they had put down their instruments was just totally destroyed. But they actually got a lot of really good information out of it. But the storm chasers go out, and that's one of the things they use these acceleration formulas for. It's a really good use of it. Race car drivers use this a lot. Those road course drivers, Le Mans, and anytime they want to know how fast they can accelerate off a corner. When they do the NFL combines, of course, they do the acceleration test, which is your 40-meter dash or 40-yard dash, right? Well, they also do acceleration tests where they change directions, called the L drill. All right? Person has to run one direction, they plank, go in another, plank, go back in another, plank, go back in another, and end up back where they started. All right? The double L. And that's part of an NFL combine. All right? It's a type of shuttle run. Because they want to know how fast a person can accelerate. Does a person have a hard time? And there's a lot of things you can tell because they measure different parts of it. Does a person accelerate better to the right or left? Or do they accelerate equally in both directions? Maybe they've got a bad knee or a bad ankle and they can't accelerate as well to the left or the right. But they didn't, maybe it didn't show up on anything earlier, but all of a sudden they're saying, hey, this guy can't run to the right. He just lost, 15 places in the draft and cost him, $500,000 because he can't accelerate as fast to the right as he can to the left. And it's not fast enough. That's why they do all that testing because, these NFL teams, they pay a lot of money for these guys to play football. So they want to make sure that they are getting a product that they can use. And it's sad to say, but that's what a football player is. He's a tool. He's a product for the team. So they want to make sure that they have the best product on the field. So they do all kinds of testing on those NFL combines. They test different. They want to know how high somebody can jump, and how high a person can jump. Actually, shows how forcefully they can leave the ground. They want to know how far they can jump out. They want to know how far they can jump up. They want to know how far they can jump on the run. All right? All those things are important. That's all about velocity vectors. Okay? And acceleration vectors. Stuff they want to know. I already said weather uses them a lot, racing. They use them for traffic control. You ever been driving along and you riding along and all of a sudden the car goes over two little bumps in the road, two little wires that looks like they're across the road, and it goes boom, boom. They're actually measuring the velocities of cars moving over that area. They do that for a reason. They want to know, what is the average car coming through here? How fast is the average car coming? What time of day does a certain amount of speed cause more accidents? How fast can a car go if you're ever on that going off of the Macon Highway there onto that big loop around off of Highway 80 on the 185 North. A lot of physics goes into building those on-ramps and off-ramps and knowing how fast vehicles can travel around them. You're going around the big clover leaf and you always see the sign of the truck tipping over, right? I've seen trucks tipped over because they tried to go around those too fast. So the actual size of that circle that a car has to make, they sit down and figure that out all with physics. Because you don't want to slow them down too much, all right? Because if you slow them down too much, it's a harder time accelerating, getting back up to speed and merging with traffic. But you want to slow them down a little bit because they're going around a turn, all right? You have to really spend some time figuring out how far that arc can be and how much the pitch of the road can be without, friction breaking off and sending that truck off in a straight line. Just like if gravity suddenly let go of the moon would just fling out into space somewhere. Wouldn't keep looping. It'd go and just gone. We could just wait bye-bye to the moon. All right? Any questions? All right, got a little bit of time right now to work on your study guide. Make sure you have them tomorrow done. Not due tomorrow, just make sure they're done tomorrow. All right? So we can make sure the answers are right, because don't you want the answers right if that's what you're going to be using on the test to help you? Oh, yeah. It has to be handwritten. No printed ones. No. No typed ones. Handwritten only. Otherwise, you cannot use it on the test. And I will take it up if you are 0. Must be handwritten. Folks at home on Mevo, make sure you handwrite your study guides, because I'm going to lock Chromebook. All right, I'm going to lock your test tomorrow, so you won't be able to use anything but that handwritten study guide. You won't be able to get to it if you don't handwrite it. All right. So make sure you handwrite it, write down the answers. Excuse me. I'll tell you what, the allergy season is going to turn into the Salem witch trials. Everybody's going to sneeze, and it's going to be like
Everybody's gonna be under house arrest.
Spanish Inquisition. No one expects the Spanish Inquisition.
How early is it?
No. It's 2:50.
You need like practice.
Do you have a trash can? The trash can?
Sit back.
If you have questions on the study guide, now's the time to ask them. Who y'all play this week?
Columbus won.
I hate them.
Did you hate them?
Same.
What?
They're Columbus.
They're arrogant. They're so arrogant.
They steal players.
Morgan, shut up.
Freshman and half.
You're literally still a Columbus person. I don't care.
I don't know. It was like 4.
Just because you come here doesn't mean you don't.
You better stay on Columbus side.
No, I'm saying I'm telling
Stay
you.
on Columbus
I
side.
transferred from CHS last year.
Huh?
I transferred from CHS.
You made a wise decision.
Yeah, I did.
No, she's not welcome here. She went to Columbus.
No, she's welcome here. We'll take her.
They're not worse than Brooks though.
We'll take everyone.
They're very arrogant.
Basically, they lie to people.
Go sit on their side, please.
They basically tell a lie to people to get people to go there and basically use it to recruit athletes who don't pass the test.
Yeah. The test isn't hard to pass.
No, it's not.
Like if you
Hogan
pass,
make you got in. Everybody
if you,
get in.
If you pass the test, it doesn't mean anything. Like
So-
a lot of people get it because they're siblings or because of sports. It doesn't mean anything.
If Hogan made you get in, just shows
Hogan's
that
actually
everybody can know.
smart. Hogan's smart. He just doesn't care.
No, that's a false statement. Hogan might be the most retarded human being I've ever met.
Literally one of my best friends.
No one cares.
About you. What'd you say? Hogan's my
He's
and I met you.
He just doesn't try.
Neither do I.
Like if you try to do
It's hard to be humble when you're as good looking as me. It's hard to be humble.
It's hard to be humble when I switch there.
I like it both. I like it.
It's hard to be humble.
Hey, Alfred.
When we go to that turkey thing, you don't switch on that. I don't know where you got that switch from.
Because, okay, so I was thinking that too, what you're thinking, right? But then, during our corner stuff, coaches were like, okay, we're gonna, like, he was saying, like, we still have to cover deep, so.
If they're strict to that side, those are very mean or we're man.
Okay, that's literally not what that's what coaches were saying.
No, that is what they're
Ryan, no.
That's definitely Turkey.
Yeah, is that the first time you played defense since freshman year?
You have to sign up on all the insurance. Or you have your permission slip. In the name of the Father, the Son, and the Holy Spirit, amen. Dear Saint Anne, you never tire of assisting those who are in themselves seeking. Trusting not in your merits, bearing your powerful intercessions, we request your help
That's not
in this
Mercedes.
present day, all its duties and responsibilities, all its situations, whether happy or anguishing. And when tomorrow becomes today, assist us anew for God's glory and our good. Amen. In the name of the Father, and of the Son, and of the Holy Spirit.
That was big.
King George, please release the
Alright, if you ain't a senior and you ain't going to, what you call it, don't leave. I had one person in here that yesterday, and I know ain't all y'all seniors, and I know all y'all ain't going to Viking Hour. I know you do. I know you do. Some of y'all just kind of snuck out on me, Juan Carlos. You ain't a senior and you ain't in Viking Hour.
It's just someone traveling, I'm
No.
trying to get ahead of you.
No.
I figured out you just have to wait. Then I'll be like halfway pulled out and the moms will keep going.
If you
and I
come
have
through like at 2:30, it's crazy how much traffic you get.
They need to let the freshmen out first, those cars can get out. That's fair.
I like that body armor water.
I do too.
Is that the pH 9?
Yes, sir. It's good.
I like it.
I don't drink
It's
water.
great after a run.
Yeah, I don't drink water, but I like this water, and it helps me drink it because
I don't know what it is about it.
A bad
It-
statement. I don't drink water. You like.
So like I drink this water, because I'm always dehydrated. So like I'm gonna drink water as well.
I don't know what it is about that pH 9 water. It's better. Deuces, y'all have a great day. Stay out of trouble. Don't do anything stupid.
Bye, Coach Anderson.
See ya.